Okay, so welcome everyone to TCS Plus. So today's speaker is Sepehr Assadi. Before I introduce the speaker, today's operator is Clement and helping us in the organization of TCS Plus are Odette Ragat, Thomas Vadik, Ilya Rosenstein, and Gautam Kamat. Clement is now going to go around the table and introduce the groups.
Thanks, Anindya. So yes, so today joining us from MIT, we've got Ben Lee Volk. Then we've got Irfan Sadekiazer from Indiana University. Hi. We have Sam McGuire from UCSD. Hi. We've got Santiago Incapié-Portes from EFIT University. And we've got Shang-En Wang from the University of Michigan. And hi. And we've got Slobodan from MIT. And yes, so.
Okay, so before we start with the talk, so 2 weeks from now, we have Sharon Obeisgaran, who will be speaking at TCS Plus. And feel free to send in your suggestions regarding other talks you want to see. So today's speaker is Sepehr Assadi, and he recently finished his PhD from Penn, advised by Sanjeev Khanna, and now he's a postdoc at Princeton and will be joining Rutgers in fall. So he's in a radius of 50 miles, he has done fantastic work in what could be broadly classified as algorithmic foundations of big data. So this includes work on streaming algorithms, distributed computation, and more complexity theoretic aspects like its interaction with communication complexity, for which he has won a number of awards, including the PODS Best Student Paper, SPA Best Paper, and a SODA Best Paper very recently. And today he's not going to tell us about any of those works, but something else. And so, Sepehr, over to you.
Okay, can you hear me, everyone? Okay, so thank you for joining in, and thank you, the organizer of TCS Plus, for this. This is TCS Plus is really great resource. Okay, so and before I begin, please interrupt me and ask questions. Otherwise, I just feel like I'm talking to myself, and it's going to be boring for everyone. So I'm going to talk about a sublinear-time algorithm for counting arbitrary subgraphs via H sampling. This is a work I had as a graduate student with my advisor Sanjeev Khanna at Penn, and also Michael Kapralov at EPFL. Well, subgraph counting is this general family of problems in which basically you have a very large graph G. Think of it as being a Facebook graph, a web graph. Then you have a small constant size pattern. Think of it as being a triangle or a clique on a couple of vertices. Let's say clique on 10 vertices. And what you want to do, you basically want to count how many times this small pattern, this small subgraph H, appear in this bigger graph G. And by that, excuse me, and by that I mean how many subgraph of G are isomorphic to H. And by subgraph, I do not mean necessarily induced. It can be any subgraph of G. I want to count how many times this subgraph appears as an induced subgraph, as a not necessarily induced subgraph inside G. So let me, for example, if my subgraph H is the target pattern, in this bigger graph G, it appears hopefully only twice in these two places. Now, this is a classical problem in theoretical computer science. We have been studying it from very different aspects. It's actually one of those problems that really has tons of application in analyzing real-world graphs. We have studied this problem from many different angles. We know very good exact algorithm for this problem, typically based on fast matrix multiplication. We know approximation, distributed streaming, many different types of algorithm for this problem. In this talk, I want to focus on sublinear time algorithms and for solving this problem approximately. So what does that mean? Typically, the graphs that we want to solve this problem for are very, very large graphs. Think of billions of nodes or trillions of edges. And so when you want to deal with such a very large graph, you typically cannot even read the entire input. What you can do is what you need to do is to try to come up with a solution which is faster than even reading the input, which is typically called a Sublinear-Time algorithm. And if you're not going to be able to read the input, you have to be able to query it in appropriate places. So you can ask, for example, is there an edge between two set of vertices, between two given vertices or not? And I'm going to, in a moment, I'm going to define this formally. But before that, let me emphasize that if you want to work in such a sublinear regime, you typically need to allow for both randomization and approximation in your solution. Okay? So now let me define the problem formally. Let's say you have a subgraph edge. This is given to your algorithm explicitly. For all this stuff, let's just assume that edge has a constant size. It's a triangle, it's a clique on 4 or 5 vertices. Okay? And the algorithm has a complete access to graph edge and it can run anything on that. Then there is this graph G, which is unknown to the algorithm. It has n vertices, and we are going to assume that actually the labels of these vertices are basically just 1 to n. So you can assume the algorithm knows the vertices of graph G, but it doesn't know what are the edges in G. And G has m edges that we can access using some queries. In particular, we can give a vertex and ask what is the degree of this vertex. This is a degree query. Okay. Okay. Is there a question on the noise or? Okay, I'm going to continue. Let's see.
Yeah, I think it was just noise. So
yeah, okay. Good. So we had the degree query. You could give the vertex, and I'm going to return the degree of that vertex. We have a neighbor query, going to give you a vertex and an integer I, and you have to return to you the ith neighbor of this vertex v. So this is a neighbor query. There is also a pair query. Given two vertices, we have to determine whether they are connected or not. So you can typically query the graph using these 3 types of queries and get the answer and use these queries to solve the problem. Let me mention that these 3 are the standard queries people typically allow the algorithms. This is called the standard graph query model. In this talk, I'm going to allow actually a 4th query, which works as follows. It allows you to sample an edge from the graph uniformly at random. In order to do that, you can think of it, it's a button, you push it, and it's going to give you one edge chosen uniformly at random from the graph. If you push it again, it independently samples another edge and give it to you. Okay. This 4th query is not a standard. It does not appear in every work, but it appears, and there are some other works before us also that consider this query. And through the end of the talk, I tell you why we are allowing this query and how can we actually remove also the need for these queries. So the algorithm has these queries to the graph. You're going to make these type of queries, get the answer, do some computation based on the answers you've received, and then output a number which should be 1 plus minus approximation to the number of copies of H inside G, denoted by sharp edge with high probability. Okay, so this is the formal definition of the problem. Is there any question so far?
Yes, so I have a question. If you don't have edge sample queries, can you simulate them?
Yeah, exactly, good. If you don't have these edge sample queries, there are 2 types of things you can do. You can either do a pre-processing. If you know the degree of all vertices, you can sample this. You can sample proportional to the degree, which gives you an edge sample. Okay, that gives you an additive term of order n. You can also, there is a nice algorithm that you can sample one edge almost uniformly at random with some overhead multiplicatively. I'll talk about it at the end of the talk. But yes, so there is a black box way to get rid of this thing at a certain cost. Okay, so this is the problem. Let me give you a quick background here. Now, more than something like 15 years ago, there's this very nice algorithm by Feige that gives a 2 plus epsilon approximation for approximating just the number of edges. Here it means that this pattern edge that you are interested in is just a single edge. Okay, and this algorithm only needs to use degree and neighbor queries. And then there was an improvement in this algorithm to reduce the approximation factor to 1 plus epsilon. Then a couple of years later, people started to look at more complicated structures, such as approximating the number of stars, again using degree and neighbor queries. And at that point, they also show this lower bound that if you want to go over much more complicated structures, such as triangles and others, then there are impossibility results that provably you cannot get a sublinear time algorithm. But a couple of years ago, there was this very nice ELRS paper that shows that if in addition to degree and neighbor queries, you also give me pair queries, now there are these nice sublinear time algorithms for approximating number of triangles as well. And recently in last talk, this was generalized to count any arbitrary clique. You can think of a triangle as being a clique on 3 vertices. This works in extended these algorithms to work for any k clique. And roughly around the same time, there is also another nice work by Ali Akbarpour et al. That shows that you can actually approximate the number of stars more efficiently if you allow degree, neighbor, pair, and edge sample queries. So allowing a stronger queries will give you better algorithms for these problems. Again, let me emphasize, there are tons of other works here. I did not mention them, but this is basically the story that is most relevant to our work. But if you look at all these works, what you see is that typically people focus on special choices of subgraph edge. Let's say they wanted to count the stars, paths, triangles, etc. What we asked was that, can we actually design a single sublinear time algorithm that simultaneously works for every subgraph edge? So we don't need to focus on triangles or cliques in particular. Can I have an algorithm that you give it as input also this subgraph edge, and it's going to just count the number of copies of this edge into this larger graph G using queries? Okay. And it turns out the answer is yes. And qualitatively, we just give a very simple sublinear time algorithm for counting arbitrary subgraphs if you allow me to make these edge sample queries also. And I want to mention it matches the performance of all these previous algorithms for stars, triangles, and cliques, and also achieve optimal bonds for many different subgraphs, such as, again, these subgraph stars, triangles, and cliques, and also odd cycles. Good. So this is qualitatively our result. Now let me try to quantify it and give you what are the numbers, basically. And before that, I have to give you a little bit more background on what is happening in the literature. In particular, I told you about this ELRS paper that achieves approximation algorithm for number of triangles. The bonds that this paper gets is that you can get a 1 plus epsilon approximation to number of triangles in m to the 3/2 divided by sharp edge, queries, and time. And there is an additive term here also. Let's, for the purpose of this, let's for the moment ignore this additive term. And similarly, for k cliques, people came up with this algorithm that makes m to the k/2 divided by sharp edge queries and also time, plus some additive term, and can approximate all number of all k cliques. And you can see if you put k equal to 3 in the second result, you recover the first one. Now, actually, if you look at these algorithms, you can partition their logics into 2 parts. There is a first part, which is let's call it an estimation algorithm. It assumes you have access to some sort of random edge samples and design an algorithm that estimates the number of k cliques or triangles using these random edge samples, with the bonds given by the first terms above. So m to the 3½ divided by sharp edge for triangles, and m to the k/2 divided by sharp edge for all cliques. So this is the first part of the algorithm. Then there is a second part. Do you have a question?
Yeah, sorry, I have a small
Yeah.
question. So here, I mean, it's parameterized by the number you're trying to approximate, right? So how exactly does
Yes.
it work in practice?
Oh, good, good. So one thing you can do, even if you don't know this number, what you can do is to start from the largest guess possible, okay? Which actually I'm going to show in a couple of slides is basically m to the 3/2 for triangles and m to the k/2 for cliques. So you start with the largest guess possible. At that point, let's say your algorithm has constant query complex. You run the algorithm, you get some number. Then you look at the factor 2, smaller than that. You continue doing that, and you can prove the only time you get a concentration is when you actually hit the correct number for h. Okay. So even though you do not know the value of h, your solution is going to still depend on the value of h. Okay. And if you continue doing this, so it may happen actually, if your graph doesn't have any triangle or any clique, you may end up to basically making a lot of code, and at the end you have to just recover the whole graph. But you don't need to necessarily know this beforehand.
Okay.
Good. Okay, good question. And now it's good. So then there was this first part of this algorithm that make this estimation assuming you have these random h samples. And there is a question, what is the dependence on epsilon? It's actually a small polynomial, typically 1/epsilon² or 1/epsilon³. Maybe some log 1/epsilon also. You do not need exponential dependence on epsilon. Okay. Like for example, in our algorithm is 1/epsilon². And by the way, throughout the talk, I'm going to use this notation O* to hide dependence on epsilon log factor. Basically, any lower order term like thing, I'm going to just hide it with O*. Good. Okay, so now to the second part of the algorithm. Remember that these algorithms do not assume they have an h sample query. So they have to construct a data structure that provides these random h sample queries for them. And that's where the second terms in these algorithms come from. They'll design some wrapper argument that actually sits on top of these estimation algorithms, make these many types of queries at the beginning, and try to provide these sort of random h samples to the algorithm. What I said here is a slightly oversimplifying this result. It's not completely a black box separation between these two terms, but roughly for the intuition, this seems like a good separation. And also one can observe that if I provide these h sample queries, you actually do not need this second term anymore. And the performance of these algorithms become more cleanly m to the 3½ divided by sharp edge and m to the k/2 divided by sharp edge times some lower order. Good. So this was what was known so far. One question right away is that if we want to generalize these bonds, before that, let's just see what are these numbers. What is m to the 3½ and m to the k/2 numbers come from? And it turns out that these numbers are actually the maximum number of k-cliques possible in a graph with m edges. So m to the k/2 is, again, if I give you a graph which I only promise to you that has m edges, the maximum number of times a k-clique can appear in this graph is m to the k/2. And it's very easy to see that you just need a graph on a clique on root m vertices to satisfy this bound. Good. But these type of extremal results like here are known for every subgraph H in a very general sense. In particular, we know that to any subgraph H, we can assign a number, let's call it rho of H, which says that in any graph with m edges, this subgraph H can only appear m to the rho of H time. And now what is this rho of H? Is the fractional H cover number of H, which is the solution to the following problem. So you have this small subgraph H. You want to assign weights to the edges of this graph such that the total amount of weight is minimized. And also every vertex collects at least 1 unit of weight on the edges incident on it. So for instance, if this is my subgraph H on the left, a fractional edge cover can put a mass of half on this triangle and 1 on these two edges, and ensures that every vertex of this graph is incident on 1 unit of mass. Okay?
And so, but this is tight, as in there's an asymptotically large graph which will have this
Good.
number.
Yes, actually, this is tight. It's a bit tricky to create this, but there is actually, if you look at our own paper also, we have to create an example. This is known how to create such an example to achieve m to the rho of h divided by some constant which depends on rho of h. Yes, this is completely tight. And there is a systematic way also to create it based on the solution to the linear, to the dual to the this linear program. You can create such graphs. Good. So m to the rho of h is the maximum number of copies of h in any graph with m edges. We know this extremal result. We also even know some algorithmic variant of such result. There is this problem which is called subgraph enumeration. Instead of finding whether copies of h exist in a graph G or not, we want to just list all copies of h in G. And for a very long time, we actually knew algorithm that take m to the rho of h time for any given graph h, pattern h, and can find this list of all copies of h in G. And what does this mean? It means that these algorithms are worst case optimal. Okay? There exists a setting of G, basically, where the number of copies of h is proportional, the output size of this algorithm is proportional to their time. Okay? So we knew optimal algorithm for this listing problem for all choices of h. Now let's go back to the subgraph counting problem. We only knew these type of bonds for k cliques. Basically, it's very easy to see that rho of k cliques is k over 2. You only need to put a mass of 1 over k minus 1 over every edge of your graph to get such a fractional solution, such a fractional edge cover. And we knew how to get m to the k over 2 divided by sharp h time algorithm for k cliques. For other subgraph h, we didn't know how to do that. And this is basically what we are going to do in this paper. We are going to generalize these clique counting arguments to work for this more general m to the rho of h type bounds. Quantitatively, so we are going to give an algorithm that, given any subgraph h, outputs a 1 plus epsilon approximation to the number of copies of h in m to the rho of h divided by sharp h times this log n over epsilon square queries and time. And we are going to assume in particular h sample queries. Okay, so is the main result clear now? Good. It's easy to see that this algorithm actually matches the bonds for previous algorithms for triangles and cliques. It also, the algorithm matches the bonds for stars, but I'm actually doing a bit of cheating here. The bond that I've written here is actually not tight for stars. Our algorithm achieves minimum of this point and another term. That term is tight for a star. So the same algorithm achieves optimal bonds for stars also. But let's not talk, I'm not going to talk about that during this talk. This algorithm achieves existentially optimal bonds in the sense that there are choices of subgraph H, such as cliques and odd cycles, when this bond is actually tight. So there is no algorithm for general H that can always improve upon the current algorithm. And finally, one important motivation of subgraph counting problems is in database join size estimation. I'm not going to define the problem, but basically it corresponds to subgraph counting when you have color on the edges of your graph, both G and H, and you want to count colorful copies instead of the normal copies that we were counting. And then actually our algorithm, exactly the same algorithm with the same bond, work for that problem. And there it is tight for all choices of subgraph H, not existentially only for cliques and odd cycles.
I have a small question. So the way you phrase it, h is an input. It looks like h is more like a big parameter, like a massive parameter. So are you penalized for the time it takes to compute row h?
Good. So so for this talk, really, let's think of row h as being constant, because if you see, it's m to the row of h time there. If row h is not constant, this algorithm is not even going to be polynomial in some sense. Okay, maybe, okay, depending on sharp h. But there is an added, so computing row h, it's a fractional solution. You can do it with linear program, but there are some other parts of our algorithm that needs exponential time in row of h. Okay, so there is at least a 2 to the row of h term here that I'm completely hiding. It's not good. This algorithm is not good if you want to go over super constant h. And by the way, it's so super constant h, this problem become NP hard immediately. You can just solve clique and things like that with that. So we typically want to focus on just a constant ratio. Okay, good. Okay, so still, I really didn't tell you what are these bonds. So I told you what is the definition of this m to the row of h and this m to the k over 2. But why should we expect them to appear in our algorithms? Let me try to give you a high-level intuition, and let me say right away that this intuition is not completely correct, okay? But it's a good intuition. And the reason is basically just by Monte Carlo estimation. Well, m to the row of h is an upper bound on the number of, let's say, potential copies of h. Okay? If I know my graph has m edges, there are at most m to the row of h many times h can appear in my graph. Think of it as being this very long list of all the potential copies of h. On the other hand, sharp h is the number of actual copies of h. And we are interested in estimating sharp h. So what is some sort of an algorithm here is to sample a potential copy of h from this very large list and check it if it is an actual copy or not. And it's very easy to just use some basic concentration result to say that the number of samples you need for doing this task is proportional, inversely proportional to the density of actual copies of h among this large list, which means that you need m to the row of h divided by sharp h independent samples. Okay. Is there any problem with this approach? Honestly, nothing of this approach will work. The reason is that you cannot just sample an independent potential copies of h. We do not have a button that we press and will give us a random potential copy. We can sample random edges and vertices. Okay. So there is one problem that we cannot do uniform sampling of these potential copies. There is another problem is that the graph G and its degree of vertices and other structure will actually correlate the different samples we have. So we cannot even get uniform samples, and more importantly, we cannot get independent samples. Still, I think this is a good intuition to say why we are going to get something like m to the row of h divided by sharp h. We are going to try to make this approach work through something other than just the vanilla Monte Carlo estimation. Good. So let me give you some high-level idea of what we are going to do here, and then we're going to go in more details later. And the algorithm is still based on sampling potential copies and estimating this density, but it's not going to be just an independent uniform sampling. Well, there are two things we need to take care of in our algorithm. The first is, before doing anything, we have to figure out what do we want to do with this graph h. It has h is an arbitrary subgraph. It is constant size, but it is arbitrary. And it's very hard to work with a completely arbitrary graph. We need to put some structure over h. And what we're going to do, we are going to use this fractional h cover to actually decompose h into smaller components, let's say odd cycles and stars. And roughly it says that if you know how to, you only need to be able to count odd cycles and stars. You don't need to be able to count arbitrary subgraph. If you can just do the counting for this decomposition, you'll get the result for everything else as well. So you'll do this. Then there is the next part and the main part. What are we going to do with this with the graph G base? Let me give you a high level. What we are going to do is this decomposition is going to give us a way of decomposing graph H into a bunch of cycles and a star. Let's define them something like a profile. So we have to sample a bunch of cycles from the graph. Let's say this green cycle here, we sample this green cycle. We sample 2 stars, and then we are going to query the edges between them to make sure that we get actually an actual copy of H inside our graph. Okay. I'm going to clarify this in a bit later in the talk. This is the way the algorithm works. So you sample something which looks like a potential copy of H. This is not going to be, you're not going to be able to sample uniformly, but we can estimate, we can compute exactly what is the probability of sampling this object, and we can reweight it accordingly. And then we have to analyze the variance of this estimator and try to reduce the variance through some standard techniques. And that is what I'm going to talk about in the next rest of the talk. So up until now, is this clear, or any questions so far? Okay, good. So now let's talk about what are we going to do with this subgraph H. Remember, our goal is to decompose this H into simpler components. And what we are going to do for that, let's just write a fractional H cover linear program. It's basically minimize the summation of edges in H, and then minimize for each vertex, and then such that for each vertex, at least you gather the mass of weight 1. Basically, summation XA has to be more than 1. Now, this word is basically just a standard linear programming ideas. First, you can prove that such a fractional solution, there is always an optimal fractional solution, which is half integral. You only need to put a mass of 0, half, or 1 on every edge. This is similar if you've seen vertex cover have the same property also. This is a standard. Now, when you have a half integral solution, what you can do is this standard procedure called cycle cancelling. Think of if you have an even cycle in the support of your solution, this fractional LP, you can start moving the mass from one edge to the next one, then reduce from the next one to the next one. Go in a cycle and basically break this cycle into a matching. So for instance, if this cycle had an even length, I could give this half from here. I give half to here. This guy will become 1. Then I reduce half from here. I give 1 and push this half to here. It becomes 1. It's easy to see that on an even cycle, you can do this without changing the weights of any vertex. And so you can change your solution into you can remove all the even cycles. If you do it carefully, what you're going to end up is a disjoint set of odd cycles and trees. And then finally, there is again a standard way of just pushing the mass of the tree into the leaf node and breaking the tree so that the tree becomes just a collection of stars. And so I want to emphasize all these parts are standard. You can just do basic linear programming to get this. What is this going to give us is a way of looking at our graph H into a collection of odd cycles and stars. So here again, I have this green odd cycle and I have these 2 red edges. So now that I have this decomposition, I want to start identifying H through using some simpler notions, basically. Let's look at this odd cycle. If I want to write this odd cycle for you, I can just give you this edge, and this single vertex. And this is going to uniquely identify this odd cycle for you. Okay, assuming I'll use a standard type breaking and write the edges in an appropriate order. But then what does this tell us is that if I want to specify any odd cycle to you, I have to give you k edges and one extra vertex from the neighborhood of one of these edges. And why is this good? It means that if I want to sample an odd cycle from my graph, I have to sample k edges and one vertex from the neighborhood of one of these edges. This is the way we are going to do this. Similarly, if I have a star with p petals, I only need to give you the center of the star with the outgoing edges. So stars are almost trivial. I'm basically going to give all the star to you. And now if I have a subgraph H, and if I give you these two edges, this vertex, these two edges, and this one edge, so that I can identify all its cycles and stars, you can actually identify the graph H itself also. There is a unique way to write H based on these profiles that I specify, which again for us translate to, if I want to sample a copy of H, I only need to sample this bunch of odd cycles, sample a bunch of stars, and then just ensure that they sit correctly with respect to each other by querying the edges between them. Okay. This is going to become clear in just one slide. Good. So now we have to see that how we are going to be able to use this and work with our graph G. And for a while, let's actually look at just solving a simple problem. If I want to count the number of 5 cycles in a graph, the first thing I have to do is to sample a 5 cycle. Remember, I said that sampling a 5 cycle means that sampling these two edges and this one vertex. So we are going to sample 2 edges uniformly at random from this graph G. And let's say these edges are sampled with an order. So U1, V1 edge is different from V1, U1, because cycle has an ordering inside it. So you'll sample 2 edges uniformly at random. You look at this vertex U1, the first vertex of the cycle. Let's say it corresponds to this vertex here. You sample one vertex from its neighborhood. This is this green vertex you'll get here. And then you are going to query all the edges between them. So to sample a cycle, I sampled 2 edges and one vertex, and I did a bunch of queries in the middle to make sure that this cycle actually exists in my graph. Good. Is there a question here about this process? Okay, great. So this is one way of the sampling a 5 cycle from a graph. Now that I'm able to sample a 5 cycle, can I use it to estimate the number of 5 cycles also? And yes, the answer is yes. You can do something very simple. Look at the 5 cycle in your graph. Now fix a 5 cycle. What is the probability that this procedure is going to sample that cycle? Well, you have to sample these 2 edges correctly, and I told you the edges were directed. So you have some probability like 1/2m squared to sample the edges of the cycle correctly. And then you have to be able to sample this vertex W correctly from the neighborhood of U1. So there is a division by 1/degree of U1. So if you fix a cycle in your graph and you look at the set of vertices, the probability that this procedure sample this cycle is exactly this number. Modulo some, again, you have to use some tie-breaking rules. Okay? So why is this good? You can use this. Now I wasn't able to sample a cycle uniformly at random from the graph, but I am able to sample a cycle with a probability that I can compute what was the probability of that sampling. So I can use it to define this random variable x. Just sample these 2 edges and one vertex. This is basically that potential copy of a 5 cycle. We sample that, and then we check by querying the edges between them, is this really a 5 cycle or not? If it is a 5 cycle, we let this random variable x to be inverse of this probability of sampling the cycle, which is, again, to emphasize, it's going to depend on the vertices you sample, because there is 1/degree of U1 here. But that is something that you can learn by just making 1-degree query. So If you were able to hit a cycle, you let x to be proportional to this probability, basically inverse of this probability. If you didn't hit a cycle, you let x to be 0. Good. So this is a random variable I defined for this procedure. What is the expectation of this random variable? Any guess? You sample the cycle. If it exists, you give a number inverse of the probability of sampling this sample. If this doesn't exist, you give it 0. So it's very easy to see that up to, again, tie-breaking rule, expected value of this random variable is exactly the number of cycles that exist in your graph. Okay. This is basically, we are doing exactly the same thing as that intuition I gave you to sample a potential copy and then check whether it exists or not. The only problem is that the potential copies that we sample are not uniform, so we just have to change their weight accordingly. But this is exactly the same thing as before, and you can show that the expectation of x is exactly the number of copies of h inside your graph. Okay? Here in this case is the number of 5 cycles. So if you have an unbiased estimator random variable for some problem, for some counting problem, you are essentially done. This part that I'm going to talk about doesn't have anything to do with our problem. Any other problem, if you want to estimate some number, you can define an unbiased random variable that in expectation is equal to that number, and then to turn it into an algorithm, you simply need to repeat that random variable independently. Basically, variance of x divided by expectation square, and just take the average. And why this works, this is just Chebyshev inequality. Okay. So basically, it says that for any other counting problem, what you need to do is to get a good unbiased estimator and also a bound on variance. And in our case, what this means is that this algorithm has time complexity, which is basically variance of x divided by sharp edge square. Sharp edge is the expected value of x. Good. So are we done then? And the answer turns out to be no, actually. We are not done here. The reason is because this estimator that I define as it is has a very large variance. It's very easy to see that the variance of this estimator is you are reweighting by 2m square each time, so you'll get a hit of 2m square. You're also reweighting by the degree of a vertex, which, because there is no bound on that, it's going to be maximum degree and then times the expectation. This is just a basic calculation. It's going to give you, this is the variance of this problem. If you're plugging in this bond here, you're going to get a bond which looks like m squared times n divided by sharp h. Instead, we want something which looks like m squared times root m divided by n. And basically, the problem with this procedure is that there are these high degree vertices that may or may not be incident on a small number of 5 cycles. But because we are multiplying by their degree, we have to pay a lot for those vertices. So let's try to fix this. And again, the way we are going to fix this is to use some sort of a standard variance reduction technique. Well, if you have some vertices which are going to have a very high variance, if you hit them, let's try to right there sample more vertices for them to reduce the variance and take the average right there instead of taking an average at the very end. So this is going to be the new algorithm. We are going to still, as before, sample 2 edges, u1, v1, and u2, v2 uniformly at random. We are again going to, okay, so for now, let's assume that these vertices that we sample, this u1, v1, degree of u1 was smaller than v1. If it is larger, you can just basically abort the sampling right away here. You'll lose a factor 2. So here, let's assume this. And remember, previously we were sampling one vertex in the neighborhood of u1. Here, I'm going to sample something like degree of u1 divided by root m times. Okay, so I sample 2 edges. Instead of 1 vertex, I'm going to sample a bunch of vertices. And then I run exactly the previous estimator for each one of them, and then take the average. Okay? So this is the new algorithm. And now you can prove that first, it is still unbiased because it's an average of bunch of unbiased random variable. And its variance is not large. Why? Previously, it was a degree of U term here. Now I multiply that thing by taking average to this number, to inverse of this number. So instead, I'm going to get a root m instead of a degree here. So are we finally done? Well, we only need to repeat this estimator, variance of y divided by sharp h square, which is m to the 2.5 divided by h. So it seems that the number of times we need to repeat this estimator is good. But actually, in some sense, we may have not done anything. What we were doing before was to do some sampling and taking some average at the end. Now we are saying take some average in the middle. And it's not clear why it should be any different. Maybe we just pushed everything in the middle, basically. And the problem is that, remember now, because we make one sample and we have to sample degree of u divided by root m time, maybe we are going to increase the time and queries needed to compute one y. And in particular, in the worst case, this value can only be bounded by n over root m, n being the max degree, and so we have to repeat it root m times, n over root m times. However, I want to claim that this is actually not a problem here. What is going to happen is that the expected cost of computing this y is not large. It's constant, you have to always pay the constant. After that, the way we calculated y was to sample an edge uniformly at random, so 1 over m over all the edges, and then pay something which is proportional to the minimum degree of both endpoints of this edge. Okay, so does this calculation make sense? Good. Now what is this number? Just summation of, this is just a combinatorial question. If I go over the edges of my graph and each time add the minimum degree of vertices on that edge, how large can this number be? It's a simple exercise. You can work it out on yourself, but also it's related to this arborosity and degeneracy of the graph, and it's easy to show that this number can never be more than m times root m asymptotically. So if this number is m root m, and we have an m to the minus half times m here, all of these things will add up to be just a constant. So what is good for us now, we are actually really done here. This estimator y in expectation only takes constant time to be computed. And so we can repeat it these many times and get an algorithm for computing 5 cycles. This is all the algorithm you need for approximating 5 cycles. And in fact, this is all you need to approximate any odd cycle. What is going to happen is that you're going to sample k edges and then pay this root m extra. And this is going to basically be proportional to the fractional edge cover number of a cycle times the expected value. So this way you'll get an algorithm for an unbiased estimator for the number of odd cycles. You can use a similar approach, it's actually much simpler for a star, and also get an unbiased estimate for the number of stars, another random variable, which its variance is m to the fractional edge cover of that star, which is here just L, basically the number of edges in the star, times the expected value of the number of copies. Good. So up until now, we design estimators for stars and estimators for cliques. And our final algorithm is basically just going to use this decomposition to merge these two estimators together. So recall that we could decompose our graph into a collection of odd cycles and stars. And we know how to compute an estimator for each odd cycle. We know how to compute an estimator for each star. We have to combine them together. This combining looks like this following procedure. So this is my first star. To sample a star, I'm going to sample these 2 edges as before. Then for sufficiently many times, as we say, degree of this vertex divided by root m times, I'm going to sample this top vertex here. Then for that, I have to go to the next cycle in the graph. Now I don't have a cycle. I have to go to the next star, basically. For that cycle, I have to sample again. I sample the edges of that cycle, and many times I sample an extra vertex. For that, I'm going to go inside that. You can see that there is this iterated loops, inner loops inside each other, equal to the length of the number of cycles and the stars you have in the decomposition. And this procedure is basically going to look like a tree that at the beginning you sampled a bunch of edges, then you branched out. For each branch out, you reach a bunch of new vertices, then you sample a bunch of edges, then again you are going to branch out to new and new edges, and you continue like that. Cool. Basically, the analysis is before you have to recursively compute the variance of this new estimator. It's not completely recursive because we didn't sample one cycle and then move on to the next cycle. We sample a bunch of edge for each cycle. Then we sampled bunch of vertices. So partial cycle, we completed it with a bunch of different way of completing the cycle by this vertex. For each one, we continue. And it become a bit messy, honestly, here. But what is good is that there is a clean way of looking at this procedure and to put this structure of the proof so that things do not become too much messy, at least. You do that, you're going to get a random variable with a variance which look like this. Variance of the first cycle times variance of second cycles and so on, and then you multiply it with the variance of the stars until the end, plus some lower order terms. Okay. And this is the bond we know. We know that variance of the first cycle is basically the number of edges divided by 2. It's m to the number of these edges divided by 2. For each star is m to the number of these edges. If we just write this thing, basically the multiplication of these numbers, which exactly become m to the row of h. And we'll get the bond on the variance that we want. Okay? Does this make sense? Okay, good. And as before, we can show that the each time computing this z is going to take constant. Now this constant is actually it's exponential in this row of h. So this constant depends exponentially on size of the graph h, but it's constant as long as h is constant. And then the final algorithm is as before. You have the estimator. You're going to repeat it enough number of times proportional to the variance, which is m to the row of h, and take the average. That's the whole algorithm. This way you'll be able to get an algorithm for counting any arbitrary subgraph using m to the row of h divided by sharp h, queries, and time. And the query we need is random h sample queries for sampling the edges of the graph. We need pair queries to sample that final vertex. We need neighbor queries to sample that final vertex of the cycle. We need pair queries to check whether h was a correct copy of, it's an actual copy or not. And we need degree queries to compute the probabilities, or the correct probabilities to reweight. So we need all these 4 queries. And so now let me try to wrap up here. And I think this is a good time. Let's try to answer this question that actually, why did we allow h sample queries? Typically, people do not allow them. And so why we thought it is natural in this context to at least at first look at algorithms which have this type of queries. There are 3 different results. I think the first one is that if you look at this problem in a practical setting, there is no reason to say you can never support h sample queries. In fact, there are many scenarios that the system you're working with is going to allow you to work with h sample queries. And in that case, if you can, this is going to make the life much easier. I want to emphasize there are systems, there are scenarios that you cannot do random edge samples. There are scenarios that you cannot even do random vertex sample, but there are also certain cases that you can do this. In particular, if you have a scenario when if your graph is just stored in the memory of your computer, you typically store the edges. And in that case, just looking at the random location of the memory is going to give you a random edge sample. Okay. So this is on its own, I think this is an interesting query that may have practical importance.
A question. So, is there like, I mean, you said, okay, so I was thinking of this kind of a graph as being too large to be stored somewhere. Is that a right way to think about this? Or no, this is not that kind of an application?
I mean, it is stored somewhere. It might be in a distributed fashion completely. It may not be on a single computer, but it might be in a distributed fashion.
Okay, okay. Yeah, I was wondering if there's like yeah.
These graphs are not typically, at least as far as I know, they are not created in an online fashion. It's not a streaming question. This graph exists somewhere. Okay.
Okay.
Maybe on many different places, but. And by the way, these algorithms are useful even in the centralized setting, even if you do not care about sublinear time. Okay. If you just want a good approximation to the number of copies of good 1 plus minus epsilon approximation to the number of copies of a graph in G, even not in the sublinear time, algorithm is going to work for you. And there you can, of course, it is on a single machine, it's in the RAM model, you can, of course, sample. Okay. There is also this point that Clement pointed out earlier, it's that even if you do not have random edge queries, you can actually obtain them at a certain cost using different types of queries. One way is to just spend order n time at the beginning, query the degrees of all vertices, and then from now on you can always sample proportional to the degree and pick one of the outgoing edges. This is going to be a random edge for you. This increases your time by an additive factor of order n, which may or may not be desirable depending on what is the other term you get. Note that this can still be sublinear in the graph size if your graph is sufficiently dense. Okay. There's also this very nice algorithm that allows you to sample almost uniformly an edge from your graph with n over root m. And that almost uniform is completely okay for our purposes as well. So we can increase the bounds in our algorithm for additive of order n or multiplicative of n over root m, which the latter one is going to be order 1 if your graph is very, very dense. Cool. But I think the most important reason I feel like it was okay to allow edge sample query is that this seems the best way to abstract out the logic of the algorithms. I told you most of the previous algorithm worked as follows. You design an estimator using some sort of random edge, and then design this wrapper for providing these random edges. If I give you random edge queries, you can just focus on designing perhaps the core of the algorithm, which is this estimator, and then later on worry about what to do with these wrappers. Okay. And that is the reason, basically, the way we were able to improve the generalized Despond to all these row of edge was to directly focus on the estimator part instead of trying to work out at the same time with this wrapper argument as well. So let me conclude. We get an algorithm for 1 plus epsilon approximation of number of any given graph h, m to the row of h divided by sharp h time. This matches all previous algorithms for odd cycles, cliques, stars. This is also tight for all these graphs that I mentioned. There are two main open questions left here. One is that I really want to know, are there graphs that actually this algorithm does not achieve optimal bounds? Okay. Even if I assume 8 sample queries. And again, we have to be careful here. The bound as I've written is not tight for stars, but the same algorithm actually achieves tight bounds for a star. So at the moment, I don't know what is a good subgraph H, which this algorithm does not achieve optimal bounds. And maybe some even cycle, because for odd cycles we know this is tight, but maybe even cycles is a different story. There is also another question. Suppose I want to completely get rid of H-random, H-sample queries. I suspect that the bound we should get in analogy with previous work is to get something like m to the row of h divided by sharp h for the estimation. Instead of plus n, we should get something which is n divided by this number of copies, 1 over number of vertices in H. The second term you can show is a lower bound for counting any arbitrary subgraph if you do not know its sample queries, but we don't know, of course, if it's tight or not. That's all I wanted to say. Thank you.
Thanks.
Thank you. Thank you.
So is there any other question for Sepehr?
Actually, I have a question. So, so there are these algorithms for counting like cycles, etc. Right? How many cycles are there? I'm just thinking of somehow like there's some work in fixed parameter tractability. Is there where you like? I mean, if there are k edges, if there are k vertices in the graph, you can always count how many copies of a subgraph are there in time n to the k.
Yes.
Right.
Sure.
And you can do non-trivial, and I believe for certain things, you can even do like polynomial in n times some fixed parameter dependence on k, like some 2 to the k. So thinking like somehow like cycle counting, etc. One of these things can be done, and for clique you cannot do it, and for clique it's fixed parameter intractable, and it's complete for FPT1 or whatever, or W1 complete, and for other things you can. So how does that, like here, what would be the analogous thing, like if you can somehow...
Good. I think one thing is that those results are for exact, as far as I know. All of them are for exact bounds, not for approximation. Okay. As for approximation, this is basically... So there is this m to the row of h term. This row of h is something between k over 2 and k typically, depending on the graph. It cannot be very small. Okay. The h cover number, yes, I think if your graph cannot be smaller than k over 2 or something like that, the best thing you can do is to pick a perfect matching. Okay. So in that sense, this becomes related also to those graphs. Yes. I don't know, actually getting bonds which look like polynomial in M times something which is like fixed tractable in this row of H parameter. I don't know, that would be very nice to get. I suspect it's not possible in this sublinear regime.
So I had another question. So here, basically, at the end of the day, the main two arguments are designing the right algorithms for odd cycles and stars. I assume odd cycles was not known in the literature, but you mentioned there was an algorithm by Ali Akbarpour et al. From last year. What happens if you use their procedure inside your algorithm?
So good. So that procedure, so our algorithm tends to be very similar for the. So good. That our algorithm and the star counting algorithm of Ali Akbarpour et al. Are very similar. If you use their analysis, it's not going to compose with the rest of our algorithm. One thing that I basically put away a couple of slides earlier, really the main part of the argument is to get these type of bounds. Conceptually, it's just multiplying bunch of cycles to stars. What is making it very difficult is that, again, we are not able to give a black box reduction to this, because it's not like I'm going to sample one cycle. After that, I'm going to sample the next cycle. The way it works is to sample partial part of this cycle, try to extending it multiple times by sampling the rest of the next cycle. So as opposed to a linear way of going, a linear way will be to sample one cycle, then the next cycle, then the next one. The way our algorithm works is that you sample part of this cycle, you repeat it many times. For each repeat, you sample part of the next cycle. then do repeat it many times, you sample the next time, and you'll, instead of a linear, it will go like a tree. Okay, that analysis seems to only work with the way we are analyzing it. Okay, does not in particular compose with the star argument. Yeah, but in terms of algorithm, the algorithms are very similar. In fact, our odd cycle algorithm is also very similar to the triangle counting algorithm, because triangle is both a tree clique and a tree cycle. So it can be seen as that sort of generalization.
Okay, well, thanks.
Sure.
Okay, so if there's no further question, we're gonna go off air. But I'd like to thank the speaker again first. So we're gonna go off air, and if you want, you can stay afterwards to ask more questions.
Yeah, thank you, everyone.